So the final part today, we're going to talk, I guess this is more of the big ideas part of the course is magma chambers, volcanology, and tectonics. And when I say tectonics, I mean the different tectonic settings that we talked about and kind of bringing it all together in those different settings. So magma chamber processes. A lot of what we talked about in this whole course is about how fractional crystallization affects the composition of volcanic rocks. And going all the way back to when we first talked about magma chambers, basically for volcanic rocks, as you evolve the melt and it crystallizes, you're seeing the residual melt, the stuff that's left over from all that crystallization, assimilation, all that kind of crap. And so volcanic rocks are basically this residual melt plus phenocrysts. Whereas in magma chambers, we see the complete opposite process, and this makes cumulates. And cumulates are mainly these different crystals that are crystallizing at different times from an evolving magma, plus some sort of melt trapped in between. In layered mafic intrusions, we see two types of layering that basically follow these differentiation trends. And the first of those is phase layering, and this is how the different minerals in a layered mafic intrusion appear with at different heights. And so this represents some sort of evolution of the fractional of the crystallizing assemblage that reflects the evolution of the magma as it differentiates. We can also see differences in the mineral compositions. So for example, plagioclase will tend to go from anorthite-rich, kind of mafic, compositions to albite-rich, which is the more sodium-rich one. Olivine does the same thing, but it goes from forsterite, magnesium-rich compositions to phthalitic, iron-rich compositions. And this is called cryptic layering because you can't just see it by looking at the rocks. You have to go and measure the compositions. The third type of layering in mafic intrusions, in layered mafic intrusions, is this modal layering, and this is we have the same kind of overall assemblage, for example, a gabbro, olivine, clinopyroxene, and plagioclase, but we're seeing variations in the proportion of minerals. You only get this kind of modal layering in mafic magma chambers, as far as I'm aware. It's not really something that you'd see in like a big granite pluton or something like that. So this is reflecting some sort of complex magma chamber process. The version I taught you, although it's still a bit disputed, is that the crystallization begins at the walls and the sides of the magma chamber where there's the maximum cooling. There's convection going on, and by either kind of falling or collapses or these density currents, then we get redistribution and sedimentation of minerals. And so in this model, the modal layer differences are like these mini crystal turbidites. Once those cores are deposited, then you get in situ growth, which is crystallization from the melt that is surrounding those cores. And some evidence for this is the cross-bedding that you see in places like Skaergård, which is clearly showing some sort of resedimentation of minerals. Another important process that I've mentioned a couple of times in the geochemistry is crustal assimilation. And this happens when hot magma, and it's usually mafic magma, melts continental crust. And so when you melt this continental crust, you then have a mix of this kind of residual wall rock plus some partial melt. And that partial melt can be added to the mafic magma, and we call that assimilation or sometimes contamination. This generally increases the silica content. It will tend to increase incompatible trace elements because the crust is quite high in incompatible trace elements. And in kind of mafic or ultramafic intrusions, we can get these kind of U-shaped rare earth element patterns where the heavier rare earths and the light rare earths are higher than the middle. So there's kind of like a bend in them. Crustal assimilation is quite common in large igneous provinces because we've got lots of mafic magma coming through continental crust, and also in subduction zones. And in mafic magmas, this increase in silica can drive this peritectic orthopyroxene formation. Another key magma chamber process is recharge. And so recharge events are identified when we get kind of like a jump backwards in the crystallization sequence, so to a higher temperature or a more primitive crystallizing composition. And so an example here from the Bushveld intrusion is that we have olivine-rich cumulates, which are usually dunite, and then you'll have these. If that magma just carried on crystallizing and it's forming orthoperoxene pyrotechnically, then we would get hartsbergites and then eventually some sort of norite. But sometimes you see jumps back, so you go from, say, like a hartsbergite or a norite composition up to a dunite again. And so the only way we can do this, because we can't just move up temperature as we're cooling and crystallizing, is if you add new mafic magma. You can also see this in jumps in the mineral compositions. So in the example here, we've got the Mg number of OPX, and you can see that generally it's going down as we go through the intrusion, upwards through the intrusion, so melt's getting more and more evolved. But there's multiple places where it kind of jumps back up, and it gets more magnesium rich, and again, this needs new mafic magma. If you have two different melts in a magma chamber, then they can mix. And this could be something like you have a somewhat evolved melt that's been crystallizing in a magma chamber, and then you get a recharge event of mafic melt. Or it could be during assimilation, we melt the continental crust, but then you actually need to mix it into the mafic magma. So we talked about this in the context of subduction zones, in that we kind of have this bimodality, like two main groups of compositions with a gap in the middle, the Daly gap. And so most melts are either starting out as mantle melts, which are mafic and low in silica, or crustal melts, which are felsic and high in silica. And often intermediate compositions are produced by mixing between these two end members. We don't always get perfect mixing. And so, especially if you have kind of lower temperature melts or two melts with very different properties, like they have very different viscosity, then they might not mix very well. And we get this incomplete mixing called magma mingling. And this is really, really common in subduction zones. There's a bunch of pictures of it on this slide say, at top right, it's an andesite with basalt inclusions. Bottom right, we have a rhyolite with these basaltic enclaves, and bits where it's kind of like tried to mix. So we get these hybrid, it's labeled as a hybrid filament there, where it's partially mixed between the rhyolite and the basaltic enclave, but it hasn't got to a single well-mixed magma composition. We can also see it on very small scales, so you'll see little enclaves of mafic rocks in way more evolved lavas. This is very common in subduction zones. Evidence of some of these complex magma chamber processes that I've just talked about, we can see them in zoning and in sieve textures. So especially in arc magmas, we will see this kind of complex zoning in minerals like plagioclase, hornblende, or pyroxenes. And in this case, in the top right, this is something called oscillatory zoning. So the composition is changing in one direction and then back again and then back again. And so this indicates some sort of change in the magma composition or a period of disequilibrium. So we're having jumps in composition or jumps in the pressure, temperature, this kind of thing. And so this can reflect a mix of fractional crystallization. We could have crustal contamination, which would suddenly give us a more felsic, a more evolved lava. We can have magma recharge, so we're jumping back to a more mafic composition. Eruptions could change the pressure in the magma chamber, or allow eruptions further up, could allow more melts to move further up through the crust, and degassing as well. Another good piece of evidence for these complex magma chamber processes is sieve-textured plagioclase, and this is where usually the core of a plagioclase gets resorbed or dissolved, and this is happening because it crystallized in one magma at a certain set of conditions, and either recharge of a new magma or decompression or some sort of magma degassing is changing the conditions around it, and that plagioclase is no longer in equilibrium with the melt, and it can be resorbed. And so you get this kind of sieve, which is the leftover stuff that didn't fully dissolve. Okay, volcanoes. We generally measure the explosiveness of an eruption using this volcanic explosivity index, which is also abbreviated to VEI. It's really important to note that this is a log scale, and basically what the VEI is measuring is the amount of erupted tephra. So tephra are these explosively erupted volcanic products, and it goes up in very big jumps. So at the extreme end, you have these eruptions like the Yellowstone caldera, which is a super volcano, absolutely enormous eruption that probably threw out about, well, more than 1,000 kilometer cubed of explosively erupted tephra. On the low end, you either get very small eruptions, or you get effusive eruptions like these kind of Hawaiian eruptions, fire fountains, where the amount of tephra is low, not because we're not erupting much lava, but because most of it is just flowing out peacefully. And tephra is only the stuff that is thrown up into the air. And this depends on all sorts of stuff, but the key ones are viscosity, volatiles, and basically the rate at which the magma rises compared to how much it's able to degas. Hawaiian eruptions are low viscosity, low volatile content melts that erupt at very high rates. So usually that's going to happen where we have high degrees of mantle melting, because that's going to produce a lot of lava, and because volatiles are incompatible elements, the higher degree of melting, the lower the concentration in the melt. So a good example are tholeiites, say in Hawaiian shield stage volcanism or in continental flood basalts. These will form fire fountains or curtains, and then these will often feed into these low viscosity pahoehoe lava flows. In ocean islands, they tend to form shield volcanoes, whereas in rifts or continental flood basalts, we'll get lava plateau, which are these stacks of composite flow fields of pahoehoe basalt. Strombolian eruptions are a bit more explosive, again, still in mafic compositions generally, but they have lower eruption rates and a slightly higher viscosity, and possibly with higher volatile content melt. So the viscosity is a little higher, but not super high. So something like basaltic andesites, or certain alkaline lavas will make these Strombolian eruptions. And in these cases, the higher volatile content is either coming from, oh, go ahead.
It was just for the name before, Hawaiian eruption. Is that like the type is called Hawaiian?
Yeah.
Is that
No, it's the type. So, yeah, I think it's named after Hawaii because that's where it was first kind of like described. But yeah, the fissure eruptions you get in Iceland would be, Hawaiian style fire curtains. Yeah. Similarly, Strombolian's named after Stromboli, but it's all over the place. So. Yeah, so where was I up to? We have high volatile contents that are either coming from this fluid flux melting, there's just a lot of fluid in the system, or again, low degrees of melting in an alkaline basalt or related lava might give us higher volatile contents. So the difference here is that the bubbles are able to move up pretty freely through the vent because the magmas are low viscosity, but they'll often get trapped near the top. That could be because there's sort of a cooling crust or some sort of mush of crystals near the surface where it's coolest. And then gas bubbles build up, and then they eventually just burst, and basically all this tephra gets ejected out in these kind of ballistic parabolic trajectories, so it's coming in a big kind of U shape, and it's just being thrown out nicely, not very explosive, and we form scoria cones from these. And it's important to remember that scoria cones are basically just the slope is fixed by the angle of repose of scoria. It's basically like a bit like a sedimentary deposit in that way. Most of the time, to get an explosive eruption in a basalt volcano, we need external water, and so these are called phreatomagmatic eruptions. If you have lava that's erupted into shallow water, the surface is very, very hot. As soon as it hits water, it's going to contract because it's cooling very fast. It'll crack, and the lava basically fragments into fine-grained ash. The water, it's also gone from being sat there, a few degrees or whatever temperature it's at, to touching, lava that's potentially 800, 1,000 degrees C, something in that range. It's flash heated to steam, and it basically explodes. So this can give us explosive features like pyroclastic flows and eruption columns that we'll talk about a bit later with the silicic explosive volcanism. And the kind of characteristic volcano style that we get from this are maars and tuff cones. So maars are these like inverted carrot shape vents into the ground, and a tuff cone is this kind of big ring of low angle, gently sloped tephra that forms around the maar. Maars often get filled in with lakes, so it's quite common to see sort of like a little lake with just this kind of low gradient volcanic cone around the side of it. Okay, moving into more viscous magma compositions, Vulcanian eruptions are basically like the silicic equivalent of Strombolian eruptions. So again, we have gas that's able to rise through the magma in a conduit, but it becomes trapped between a cool cap or plug. This is much more brittle because it's a silicic magma, it's much more viscous, and so it fails explosively. It's not just like we have this slug of gas bursting and throwing everything up. There is actually kind of like a bit of a boom. They tend to be these kind of intermittent, like every so often, moderately explosive eruptions. So these have a VEI somewhere around 2 to 3. You get a plume of ash and volcanic gases that comes a little way up into the atmosphere, but not particularly high. Yeah?
Do they create scoria cones as well?
No, they don't. Yeah, they are part of what creates stratovolcanoes. Yeah. Yeah.
So is that the difference between Vulcanian and Strombolian eruptions?
Yeah, pretty much.
That they don't produce
Oh.
scoria cones?
No, it's to do with the fact that it's more viscous. So with the Strombolian, you can think of it as like the gas is getting trapped, but it's not like a completely solid high viscosity crust. There's just, you'll have like a big bubble and it basically pops, and then this still ductile magma, you can actually kind of see it in here. The stuff that's being erupted is still red hot, and it's still it's basically arcing through the air and just falling down. Whereas with these Vulcanian ones, you have this quite like viscous, cool, like you can think of it as being quite a solid cap. And when the gas builds up underneath that, it explodes much more. It's much more explosive, but essentially the process is the same. We just have a more brittle, more silicic, more viscous magma. So
you will find like bombs from the Strombolian eruption afterwards,
yeah.
and from here you will find some scoria or...
Yeah, well, this would usually be like pumice or something like that. And so with the Strombolian one, you're never going to get one of these big volcanic plumes. You can see there's some gas and maybe like a tiny bit of ash, but this is all pretty small scale, and they're quite frequent eruptions from Strombolian. It's named after Stromboli, which is a very, very active volcano, but it's not particularly dangerous. These Vulcanian ones do produce a big like ash and gas plume because they are much more explosive. But yeah, the underlying process isn't that different. All right, pyroclastic flows. So the more explosive eruptions, and these are Palaean and Plinian. I'm not going to go over Palaean again because I didn't have a lot to say about it the first time, so I'm not going to add to it now. These produce both pyroclastic flows and surges. So pyroclastic flows are density currents of hot ash, gases, crystals, and lithic fragments. We talked about that with making ignimbrites. They flow downhill because they're denser than the surrounding air, and they move incredibly fast. They're very hot. They're probably the biggest hazard from volcanic eruptions. Very, very destructive. The main difference between them is that pyroclastic flows are very high density, whereas pyroclastic surges are much lower density. And we talked about that in the lectures with making a base surge compared to an ignimbrite. The base surge is basically just ash. It's very well laminated. This is very fast flowing. It moves ahead of the pyroclastic flow, and it gives you this kind of like upper plane of flow regime, or sometimes cross-bedded ash deposit. The pyroclastic flows they're carrying much more rock. They're much, much denser, bit slower moving, and this gives you your ignimbrites. There's a number of ways we can form pyroclastic flows, but the one we'll talk about most in terms of the Plinian ones, and that's a collapse of an eruption column will then create one of these density currents. Plinian eruptions form due to this kind of feedback of volatile exsolution. So we have volatiles that are exsolving from the magma, but the magma is too viscous and they can't escape. Now, if the ascent rate is low, then it's possible that these volatiles end up escaping through cracks in the magma because it's quite viscous, and basically it can degas gently, and then we might end up with a relatively degassed rhyolite or dacite or andesite that can go on to make a lava dome. But if the volatile exsolution is fast enough or they're not able to escape, then as we grow these bubbles, the magma is now less dense than it was when it didn't have any bubbles in it, right? We're also degassing, so we're making the magma more viscous. So that can actually make the magma rise because it's buoyant. And then as it depressurizes from rising, that can drive more volatile exsolution, and we get this positive feedback where the more the volatiles exsolve, the less dense it gets. The more it moves upwards, the more volatiles exsolve. And then you get explosive fragmentation, either when you hit this critical bubble fraction of 75%, or when the strain rate gets too high and essentially the whole thing shatters. So these cause huge volcanic plumes that can reach up into the stratosphere, about 45 kilometers high. And eventually when the eruption starts to slow down, it can no longer sustain that eruption column, and the column collapses back on itself, and then that's what causes the pyroclastic flows. In terms of the volcanic explosivity index, they go from about a low end of 4, and these so-called ultra-Plinian eruptions, these are things like the Yellowstone caldera, can be as high as 8. And so kind of all of those things, both the formation of lava domes, the Vulcanian eruptions, and Plinian eruptions, put together can make a stratovolcano. And these are also called composite volcanoes because they are composite between all these different eruption products. So to make these, you need a more viscous magma that is capable of explosive eruptions and producing pyroclastic flows. And stratovolcanoes are basically interlayered viscous lava flows and domes near the top, and then pyroclastic deposits. Lower down, away from the top of the volcano, you just have these pyroclastic materials and stuff that is eroded off the volcano. So these are kind of the opposite of shield volcanoes. They're quite steep at the top and then shallow at the bottom. Shield volcanoes tend to be pretty shallow at the top, and then if they flow into the water, then they actually get a bit steeper. Yeah, and often you'll see stuff like this. This is from a stratovolcano. It's got a huge summit crater, and it's actually got a lava dome growing inside the crater. So we have this alternations between different styles of volcanic eruptions at these, but to make a stratovolcano, it has to be capable of these explosive eruptions. Okay, I think this is the last volcanic landform to talk about is caldera formation. And this can happen after large Plinian or these kind of ultra-Plinian eruptions. And basically from the eruption, you've partially emptied the magma chamber and it's at quite low pressure. And it can even get to a point where it's at lower pressure than the surrounding rock. So what happens then is the roof of the magma chamber can collapse, and it collapses along ring faults to make this kind of round shaped depression, and that's the caldera. These will sometimes get filled in by lakes, or like the one we saw in Spain, it'll be like a large planar, roughly circular area surrounded by some slightly higher bits around the edges. Okay. Last part, tectonic settings. So we're just going to take each tectonic setting one at a time and talk about what the features are and how it all ties together. So starting with mid-ocean ridges, we started with this in the course because mid-ocean ridges are the most simple setting in terms of magmas and volcanism. At a mid-ocean ridge, we have rifting because the two plates are moving apart from each other. And this means that the asthenospheric mantle, that's the hot convecting mantle beneath the more rigid lithosphere, is able to rise to very shallow depths. Because it's decompressing so much, and it's moving along one of these adiabatic gradients. So this is just, it's not losing heat, but it's cooling because it's depressurizing. However, even normal temperature mantle will eventually melt, and that's because the solidus temperature drops faster than the adiabatic ascent path. So a typical mid-ocean ridge, this potential temperature, this is our way of comparing mantle temperatures from different depths, of about 1300 degrees C, will hit the solidus and we'll get maybe about 20% melting as it rises. Yeah, so because we're able to decompress to very low pressures, then you can get high degrees of melting, and this produces, it's shallow and it's high degrees of melting, so it produces large quantities of tholeiitic basalt. Because the normal asthenospheric mantle is depleted, then the rare earth element patterns of mid-ocean ridge basalts tend to be a bit depleted, so fairly flat with a bit of a drop off towards the light rare earth elements. And that's just because the depleted mantle has basically, over Earth history, been depleted by formation of the continental crust that is very enriched in light rare earth elements. What happens to these magmas is most of them will actually become, they'll be intruded to make oceanic lower crustal cumulates and sheeted dikes, and then a bit will be erupted as basalts on the surface. So we have this kind of like fairly fixed stratigraphy in an ocean ridge where we have pillow basalts near the top and maybe some sediments draped over the top of them. Then there's some sheeted dikes. This is formed as the crust is moving apart. You have dikes intruding one another over and over again, so it's this massive parallel dikes. And beneath you have these lower crustal gabbros and ultramafic cumulates that are formed basically by some sort of mush or stack of magma chambers in the oceanic crust that is dropping out of these cumulates. And we can see the stratigraphy preserved in ophiolites, which are abducted slices of oceanic crust that are pushed up onto the continents. We have low viscosity basalt with low volatile contents. There's no crust around because we're making all the crust from scratch here. There's no continental crust. So we don't really see much in the way of silicic melts. You can get very small amounts of these weird mid-ocean ridge granites, but in general, it's overwhelmingly mafic rocks and basalt. Because these are erupting at fairly high water depths, then they're erupting in quite high pressure. We don't exsolve as many volatiles, and so basically we just have this low viscosity, low volatile, not many bubbles, and we make pillow basalt from the rapid cooling. Go ahead.
What's the difference in N-morb and an E-morb?
Oh yeah, so N-morb just means normal morb, and that's something that people have tried to define as like an average morb composition. And then E-morb is called enriched morb, and I think, as far as I understand, people used to think that these were patches of enriched mantle within the depleted mantle. I think there's some debate now about whether those are just formed by slightly lower degrees of melting, maybe just slightly off the ridge axis, not right underneath it. And I think that's what they've drawn here. You've got the main amount of morb that's coming right up into the ridge, and then you've got these smaller amounts of melting at the sides. So, yeah. All right. Ocean island basalts and all of the kind of big ocean island and hotspot tracts are formed by plumes. Mantle plumes are these, lava lamp-like, but they're solid. The hot rising jets of mantle, and they tend to make this kind of, mushroomy shaped head followed by a thin trail behind. It's still adiabatic decompression melting, but because the temperatures are much higher, this melting, we basically moving up an adiabat of a mantle plume that might be, a couple of 100 degrees hotter than the mid-ocean ridge. We intersect the solidus at a much greater depth, and so we can start melting earlier. But if we're forming an ocean island beneath a thick oceanic lithosphere, we're not beneath a ridge where the lithosphere is very thin, then the melting actually gets cut off. And so what we get then are either tholeiitic or alkaline basalts, depending on both the temperature of the plume and where we are relative to the center of the plume. So in the middle of the plume, it might be very hot, and so we can have high enough degree of melting to still make a tholeiitic basalt even though we're at quite high pressure. Near the edges, the plume will be cooling because it's interacting with normal mantle that's at lower temperature, and plumes might actually bring some of this normal mantle into them. So you kind of have this zoned temperature. Go ahead.
What do you mean by cut off?
Oh, once we hit the lithosphere, we can't keep rising. So the mantle rises, starts melting, and then the mantle basically, it's almost like it hits a roof and it has to spread out laterally. So you can't have any more adiabatic decompression because we're not decompressing anymore. Yeah. So towards the edges where it's a bit cooler, we might still have melting, but much lower degrees of melting. We're hitting the solidus later, and we're not producing a high degree melt. And so because it's at high pressure and a low degree melt, then you'll get an alkali basalt. We talked about this in the context of Hawaii, where you have this kind of clear sequence in the volcanism. So when the plate, a new part of the plate, first moves over the edge of the plume, we're having low degrees of melting, and we get these small amounts of alkali basalt. As the plate keeps on moving across, once you get over the center of the plume, you'll get high amounts of tholeiitic basalt because it's hotter and we've got more melting. And then as the plate keeps on moving, we get to the other cool edge of the plume, and we get these post-shield alkali rocks. And in Hawaii, they have this additional stage that they call the post-erosional alkali. But these are kind of the same idea, as we're at the cool edge, there's not as much melting going on, and we're getting alkali lavas. So in general, in ocean islands, we're producing low viscosity mafic melts, either alkali basalts or tholeiitic basalts. They're not very explosive. The volatile contents can be a little higher than mid-ocean ridges, and that's partly because we might be bringing in some more, some recycled water or other volatiles that have been pushed into the deep mantle through subduction, or even kind of primordial volatiles that have been there since the Earth's mantle formed. But again, because the alkali rocks form a lower degree of melting, they'll tend to have higher volatile contents. So the main stage volcanoes, as I've already mentioned, they're shields, the tholeiitic shield stage. The late stages can be these scoria cones or potentially thin alkaline flows. And that just is going to depend on the exact volatile content and viscosity. We can also have quite variable rare earth elements because there's different degrees of melting. So tholeiitic high degrees of melting, more kind of lower rare earth element concentrations, whereas the alkaline ones can be quite enriched in light rare earth elements because we've got low degrees of melting. The most incompatible elements are more enriched. There's also, because of recycling from subduction and then these materials being brought up in the plumes, then the sources can be more enriched than mid-ocean ridge basalts as well. Okay, continental flood basalts. Again, these are plumes, but because it's coming up beneath the continent, we more commonly get rifting above the plume rather than beneath an ocean where the plume you can almost think of the oceanic crust as being a bit more competent. The plume hits it and just kind of spreads out. Whereas often a plume that comes up beneath a continent will actually trigger continental rifting. One of the examples we talked about in the lectures there was the Iceland plume, and that seems to have triggered the rifting of the North Atlantic. So we got the very high temperatures, but we've also got rifting, so we can have decompression to quite low pressures. And that means we have high degrees of melting. And so a lot of these magmas, though, because there's continental crust above them, they don't just kind of make it straight up to the surface. We'll have this extensive plumbing system of dikes, sills, layered mafic intrusions, where the magma is moving upwards, crystallizing a bit, moving up a bit more. And there's a lot of differentiation. So because there's high degrees of melting, we produce a lot of lava. But because of all this differentiation and all the kind of plumbing system it has to work its way through, a lot of continental flood basalts are quite evolved. So they're relatively low magnesium basalts. They might typically have fairly flat rare earth element patterns because of the high degrees of melting. But if they crystallize a lot, then those rare earth element patterns will be at higher concentrations than something like a mid-ocean ridge basalt because they're quite evolved. They can also be a bit enriched in light rare earth elements because of crustal contamination. And because we have these just huge volumes of magmatism, then we get these large igneous provinces, which is the combination of all the lavas erupted at the surface and all the intrusions below the surface. We're mainly erupting tholeiitic basalt, which is low viscosity, low volatile content. And so that makes these lava plateaux, which are composite Pohoi flow fields that are usually erupted through fissure vents. This is that picture from Iceland again. And here are the Deccan traps, where we just have stack after stack after stack of tholeiitic basalt. We also see layered mafic intrusions, part of the plumbing system, like Skaregard up in the top right. And there is some silicic volcanism because if it's being erupted through continental crust, then we can melt the continental crust. So this is something called, that people refer to as bimodal volcanism. We don't tend to see andesites here. We basically just get basalt and felsic rocks. All right, and then subduction zones. In a subduction zone, we have oceanic crust subducting under either continental crust, which is a continental arc, or other oceanic crust, which makes an island arc. As the slab subducts, all these fluids that were introduced during hydrothermal alteration of the oceanic crust start to get released. And so the fluids are kind of locked up in metamorphic minerals, and as they heat up, they break down, water is removed, and it triggers melting. So the reason it triggers melting is because the wet solidus of the mantle is lower than the dry solidus. So we can think about that is if we have some mantle wedge that's say 100 kilometers about 1,000 degrees C, we're nowhere near melting at the dry solidus, but if we add water, we're now dealing with these wet solidi, and you can actually get quite high degrees of melting. The fluids that are coming off the slab are stripping these fluid mobile large iron lithophile elements from the slab materials, but they're leaving behind all the high field strength elements. And so this gives us this signature of enriched large iron lithophile elements compared to the high field strength elements in the mantle wedge. When you then melt the mantle wedge, this all gets passed on to the arc magmas. Some other elements that get enriched are thorium, uranium, the light rare earths, and strontium. And so this fluid flux melting makes either calc-alkaline basalts, that's more common in continental arcs, or something called an island arc tholeite in an island arc. There are loads of volatiles because of all the fluids, and because we have this fluid flux melting, we can actually reach quite high degrees of melting. There's another zone where you get a fair bit of melting in subduction zones, and that's in this back arc region. And what's happening here is the subducting slab, it's not quite moving along, it's not being injected, it's kind of falling into the mantle. And as it falls, it rolls backwards. We can't have a gap, so basically our arc moves with the falling slab to stop opening a huge hole in the ground. And this produces extension in the back arc. So in the back arc, you'll tend to get a bit of adiabatic decompression melting. These kind of back arc basalts that you get, they can be tholeiites, they can be alkaline basalts, and sometimes they do have relatively high volatile contents, just because some of the fluids are making it all the way out here. But it's not fluid flux melting in the same way as beneath the main arc. Once we get into the crust, particularly in continental arcs, there are all these complex assimilation, fractional crystallization processes. There's loads of crustal melting going on. And so this starts in this lower crustal mash zone, which is melting assimilation and something else that I can't remember. And so we're adding all this basalt or basaltic andesite to the crust. Some of it's crystallizing, some of it's melting existing kind of cumulates or intrusive rocks down here. These are moving up, melting the crust further up. Everything is differentiating, assimilating, and you have this really, really complicated plumbing system. So we get a really wide range of magma compositions. At one end, we have the basalts and basaltic andesites that make it up to the surface quite quickly. And at the other extreme, you have actually pure crustal melts, like these rhyolites that are just made from melting the crust with mafic magmas, but they don't mix together very well, and they're just erupted like that. Because of this, we also get this huge range of types of volcano. In the main arc, it's often going to be stratovolcanoes or calderas, because we have all these explosive eruptions. Do you have a question there?
Yeah, I just want the units named up here about 3.2 kilometers per second.
Oh yeah, so these I think these are seismic velocities. So what they're detecting here, this is some sort of magma chamber or melt-rich zone where it's got lower seismic velocity. Yeah, but more one of this diagram for you can see this kind of like stack of different magmas being formed. Yeah. So the main arc, there'll be lots of stratovolcanoes because we're getting these explosive eruptions, these more evolved compositions. In the back arc, where we've just got adiabatic decompression melting, you can get pillow basalts if there's enough water, or lava plateaus. And basically we can have, pick any eruption style you want. Explosive eruptions are common, and most of the big eruptions and kind of dangerous active volcanoes on Earth are from arcs. Mount St. Helens is on a continental arc. The Taupo volcanic zone that we did the practical on is an arc in New Zealand that's had some very explosive eruptions. So, yep. And that was everything. All right. Yes.
Going back to like the fourth slide about phasing layering.
Yeah.
Can you maybe quickly just go through that?
Yeah. So this was the example. This diagram's the example that we covered from Skagergaard, and Skagergaard's a relatively closed magma chamber system. So essentially, we intruded a bunch of melt, and then it just sat there and crystallized. Maybe a bit erupted out the top, but pretty much one blob of melt that just crystallized. And so, as we deposit all these crystals, we get a gradual change from mafic compositions at the bottom to progressively more evolved compositions as we go up. You actually see the same thing in the wall rocks and the roof rocks.
Oh, so that's rocks that's around the melt, the blue and the purple.
So right now it's completely frozen, but you can imagine that it would have started as this big magma chamber and it's basically getting filled in from the edges. And most of the crystallization is starting at the roof and the walls because that's where the cooling's happening. But because these are unstable and they collapse and we have all these density currents and crystal sedimentation, the floor sequence ends up being the thickest. And what I mean by the phase layering is that at the very bottom, it's just olivine and plagioclase. Then we start to crystallize augite, clinopyroxene, then magnetite, and then olivine actually stops crystallizing for a bit. So here it's a troctolite, here it's a gabbro, here it's a gabbro with iron titanium oxides. Then it's still a gabbro, but we've lost the olivine. And then olivine comes back in. So this is a phaolite-rich olivine. So the magmas continue to get more evolved, and the mineral assemblage is changing. Here we have apatite, which is the phosphorus, calcium phosphate mineral. And then up at the top, the very last stage is to crystallize, and we see that at the bottom, at the top it's the opposite sequence, it's crystallizing inwards like this, and at the sides it's coming in from the side. And at this sandwich horizon, which is where all the bits meet, this would have been the last melt to crystallize. And it's this really, really weird evolved melt that has stuff like ferrobustamite, which is a type of wollastonite mineral, and you even get quartz and potassium feldspar. So this is like extreme differentiation seen in the mineral assemblages. You have another question? Or
Yeah,
shall I?
it's just the blue, like what is happening is going inward because from the bottom it's getting more evolved, but like on the side it doesn't have like a specification of what the composition is.
Yeah, it doesn't. I think that's just for space, because this is kind of like more of like a stratigraphic column style. But you can follow these. LZA corresponds to this LZA star. So where it's a troctolite here, and it's a troctolite here, and it's a troctolite here. And then here it's the weird evolved ferrobustamite bearing thing, and here it's the weird evolved ferrobustamite bearing thing. Yeah. So that was the phase layering, and then similarly you get this cryptic layering, and the one that they use to measure the differentiation in Skagergaard is just a plagioclase composition. So in the early stages it's this anorthite-rich plagioclase, and the AN is progressively dropping as more and more of the melt crystallizes and it gets more and more evolved.